Hi friends, so we are into our subject on risk conscious operations management, okay, for complex engineering system. We in previous lecture we understood what are complex system, what is risk conscious culture and all that. Now in this lecture, this is first week and this is second lecture, and we will be discussing the core module of risk conscious operations management, and that is probabilistic risk assessment. So lecture 2 and 3, that means this lecture and next lecture, we will be dealing on probabilistic risk assessment. Why I devoted 2 lectures? Because this is very important, how we model the risk and what are the role of process system, safety system, and finally how we obtain the risk at quantified. Probably some of you will have the experience of lifetime in modeling risk, because these two modules, these two lectures will give you a very good overview, and then there is a separate module or week for probabilistic risk assessment, where we will be dealing with this subject in a very detailed manner. I am Professor Prabhakar V. Vardhe, and I am delivering the NPTEL lecture. So let us get on to the subject. Well, first I will give you the definition of the course, then perception of complex system and plant that we have discussed in our previous slide, but then how it is related to our PRA modeling and all. So levels of PRA will be discussing, PRA procedure steps, and then adoption of plant hierarchy for PRA. And in next PRA lecture, we will be discussing the calculations that are done for understanding PRA. Okay, so what is the definition? Probabilistic risk assessment is a relatively new area. It got evolved after somewhere around, Farmer was the first one to introduce this subject, and later on for citing thing and all, and now it has become part and parcel. I can tell you how it is widely used. There are over 430 nuclear power plants world over, and most of them they have level 1 PRA, and to some extent level 2 and level 3 PRA also. So that kind of popularity is there with this subject. So I will need your full attention to understand the risk conscious operation management, because operation management is part of any industrial ecosystem or finance ecosystem or any system you can give it. So PRA, the definition is like a comprehensive structured approach to identify potential failure scenarios, constituting a conceptual and mathematical tool for deriving numerical estimates of risk. So what you understand from here is, we start building a model from individual component towards giving estimate of risk. Okay. So there are many definitions. This definition I have picked up from IAA glossary. Okay, but then US NRC, United States Nuclear Regulatory Commission, they have definition which gives not totally different, but it presents the PRA procedure in a different way. What it says is, PRA to estimate risk by computing real number of to determine what can go wrong, how likely it goes on, and what are its consequences. Thus, PRA provides an insight into the strength and weakness of design and operation of maintenance. So, the US NRC definition in terms of processes. It explains what can go wrong, how it can go wrong, and that you have to model and all. But then I have adopted this available definition, these two and many more, for the purpose of risk-based engineering and risk conscious operation management. A comprehensive, systematic and structured analytical approach to postulate the potential accident scenario by considering numerical data on likelihood and consequences for arriving at quantitative estimates of risk. Quantitative estimate of risk. Safety doesn't have a notion of quantification, but when we talk about the risk, it is a mathematical parameter. Please understand, it's a mathematical parameter. So you get numerical estimates of risk, and that leads to identification, prioritization, where the chances of arbitrariness is lesser, because we are going by numbers. Okay, and there are many more benefits, and then PRA provides the strength and weakness of the plant. So one PRA you do, and if you are revealed or you come to, it could be a system, it could be human factor, it could be any common cause element. So that that leads to, or some area which was ignored because when during initial stages when we did modeling, started the plant, so those things, left out areas also get covered into the things because they form part of the plant. Okay. So this is the definition, and with this definition we get going. So as I was mentioning there, safety critical system, from the point of view of risk assessment or safety assessment, we have to divide plant into two parts: process system, safety system. There are many more other categories: safety system, safety support system, okay, and so many other things. But let us, at this point of time, let us keep process system which are required to operate the plant for achieving the deliverables. Second part is safety system. Safety systems are basically those systems which remain standby during plant operation when plant deliverables are being achieved. But then if any situation, any deviation is encountered by the plant, which happens, is called anticipated operation occurrences. So if you encounter anything, then those deviations to be corrected, and the safety system comes into the picture and bring the plant to the safe state. It could be shutdown state, it could be partial shutdown state, but then those actions are required and it cannot go unchecked actually. So safety system plays a vital role. Sometimes they are called engineering safety features, sometimes safety system, but they are all meaning to ensure safety of the plant. Now safety assurances we have to achieve in perpetuity. So what we have done is process system, normal operation, and then any deviation. So what we are doing is we are achieving safety assurance, or we have a intent of achieving safety in perpetuity, because these two situations we have covered and we have ensured that no more unlikely events will happen. Okay, but probability as less or more, that is our assurance at a given point of time. Okay, and then one of the feature of this complex system is automatic logic. But then it is a very tricky computation understanding. We cannot provide automation everywhere. So we can provide automation for 70% of the plant, but some areas still remain on human. This is a very complex thing. Probably it doesn't call for explaining those points, but everywhere you must understand, everywhere automation cannot be done. Some areas are judged by human and actions are taken, and whenever it is required, these two modes, autonomous operation and controlled operation by human, they can be chosen, and there should be this should happen very seamlessly actually, so that they are not inducing a new event into the plant. So okay, let us come back to our topic, that is PRA. So PRA requires safety modeling, safety system modeling, and then it requires evaluation of frequency for process system failure also, and again understanding of the failure of the process system, because once the process system failure are encountered, safety systems are called, or any disturbances are encountered in the process system like power failure, and many scenarios are there. So you have to bring back the plant to the safest state. So what happens is, when you talk of PRA, all the data, model, everything is available from the plant, and we develop a level 1 PRA. Level 1 PRA, actually level 2 PRA, level 3 PRA, they are specific to nuclear industry. Why? Because nuclear industry, unlike process industry, they have a containment. So that means if accident happens, no consequences will be there in the public domain, and public area will be safe. It will remain limited to the system only, system failures. So level 1 PRA means, let us call system failure in simple words, and system means the damage or core damage frequency. But level 2 PRA deals with when something has happened in the system and there is a threat component in the containment. I told you containment isolates the plant from the rest of the atmosphere. So that means there are potential consequences in the containment, and that's why level 2 PRA is done. And level 3 PRA is potential consequences into the public domain. Actually, accident has not happened. The plant has been built, and right since design stages, level 1, level 2, level 3 PRA are done. Why? Because we have a strength assessment of strength and weakness of the plant, and wherever improvements are required, we do it. So all the 3 levels of PRA are done. Maybe in detailing and all that they might differ, but level 1 PRA definitely, which is the source of hazard, it is done for all the plant. And I mentioned that for most of the 430 plant which are there, level 1 PRA is there. Level 2 also to some extent, and now regulators are enforcing them, and level 3 PRA for some plants is available. There is a concept called limited scope PRA, which does level 1 PRA as a full, level 2 PRA limited scope, and level 3 PRA from that limited consideration try to estimate the risk into the public domain. So this is one of the best approach. Many times, and in fact I have done in my professional life, that I have done limited scope. So there level 1, level 2, level 3, all the 3 are covered, and we have a good understanding of for a most important event, what could be the potential consequences in the public domain. So now you understood that there are 3 levels of PRA, but mostly we will be detailing in this lecture on level 1 PRA only, because that is applicable to most of the industries. Okay. Okay. So once PRA, we are talking about what is the procedure. The procedure is, first a decision should be there at the organization level that PRA is due, because it requires a lot of resources. So and then certain criteria, certain report, this is called project reports, they are issued, and a consensus is formed, because PRA is a very expensive proposition, and that requires all the supports, and sometimes lab support, sometimes peer review support, sometimes performing PRA itself, not sometimes, this is at the core of it actually, And then plant familiarization. The more we are familiarized, are intimately connected to the plant, the better will be the PRA. A simple example I will tell you. The plant data, the data which is going to build the PRA, there are generic data sources available. If you take the data from generic sources only, in all the data, of course, during design stage it is required. But if we take the data, but then that will reflect on the output of the plant. Okay. So as soon as the plant has started operating, try to collect as much as data as possible from the plant, and that plant familiarization, it helps a lot, not only in data but understanding the plant, its behavior. And then once we do that, then we come to the third stage, that is list of initiating events. Okay. And then initiating event analysis start. Initiating event means what? Let us say power failure is one of the initiating event. What will happen in the plant if the power failure is there? Definitely all mega pump, big motors, they will shut down, so it will affect cooling and all that. So how shutdown systems should take? So initiating event analysis forms a very important component of PRM. And once we do that, then at qualitative level, accident sequence analysis is also done. And of course, later on it follows by safety system. I told you safety systems are redundant. They are in passive mode. Only they will get acted when any deviation or transient is there. Okay. So now safety system failure, then failure criteria. What you will call failure? And this question starts right from the component level to subsystem level, to system level, to core damage. That is a risk estimate when we give for the plant. So at plant level, then system modeling is done. Data collection. Now data collection is done at this stage because we want to have a quantified model of the plant, and then probably you'll have, if you are attending this course, there is some phenomena called common cause failure. In one word, we built our plant having a lot of redundancy. But this common cause failure, that means one cause, one failure in the plant which disables all the redundancy partially or fully. Okay. So that's why the common cause failure is a special field we'll touch upon as and when required. And next challenging field is human reliability analysis. So as I told you, this particular component will be more important. There will be a dedicated week on this, because here consciousness with human reliability, and then a model has been developed. We'll discuss that model, its strength, its limitation, and then we have quantified accident sequences, and finally the result of the plant, that is core damage frequency or risk level from the plant. That way you can understand, because CDF, this core damage frequency, is very specific term for nuclear industry, and I come from nuclear industry, so I am using it. But for every plant there can be a term, what is the damage state for the plant, we can say it that way. and then PRA and documentation and all, and then you submit, you draft a report, which is like, almost like running into 1000 pages or 2000 pages or 5000 pages. So that is the size of the PRA model. If it is a small plant, at least you expect 300 to 400 pages actually, So this is where PRA major steps we have discussed. In this lecture, we will remain limited to qualitative level. In next lecture, we will go to the quantification. So as I mentioned in the previous lecture, now we are trying to generate a list of initiating event. It is called PIEs, that is postulated initiating event. So postulated, this P, not preliminary, it is postulated initiating event or preliminary list of event. So deterministic safety and so for how these events will come, PRA comes after this deterministic approach. So deterministic studies, they will have already a list of initiating event, collect some more event from the from generic sources, then preliminary hazard analysis, plant specific analysis, review and from the similar plants, and master logic diagram and human induced events. So what I am trying to do, because if we need a very robust and quality PRA, the list of initiating event should be as complete as possible, and these are the different sources we can visit and fine tune our list of the initiating event. Okay. Now, once we have got collected all the list of initiating event which we think is applicable for our plant, we will apply a screening and grouping criteria, because they could be in terms of 100 or 200 or maybe 150. So some screening is required because we want to touch the core model of the plant. Okay. So then qualitative considerations are there. Some event may not be applicable to our plant. Then quantitative screening criteria, if our criteria is less than 10 to the minus 5 or 6, if anything going beyond that will not be applicable to us or our scenario. Then preliminary analysis results, inclusion of additional event based on internal and external condition. So this is actually ongoing exercise. Even during review, you might encounter that 1 or 2 events we have missed, and there are 2 categories of event: internal event and external event. So here we will see this list of the internal event. So again, a reference of nuclear industry I am giving you, loss of coolant accident, because core cooling, reactor core cooling is required, and core has to be cooled for the full capacity or during operation or part capacity when they shut down. So that is done by safety system. So loss of upside power is one of the transient. You might think how loss of power failure can affect, but we will see during the course. If power failure happens, what kind of events they can contribute. At least in our estimation, it has been seen that even loss of upside power, it contributes from 10% to 50%, or even say 7 or 8% to 10-15% to the total risk from the plant, and that we will see how it happens. Loss of regulation accident, anticipated, there are accident condition, loss of coolant is accident condition, but there are some transient, like loss of upside power is anticipated transient, and there are so many lists of ATWS, those form part of it, and internal fire and flood. And then finally you have external source, then seismic, and if there is a earthquake somewhere, tsunami, then flood, fire, flood, storm, all this condition or transient we have to take into account to demonstrate safety of the plant and safety of the people actually, So that's how we have it here. And now once we do that, that is, we have list of initiating event, then we start doing safety system modeling. Now we have got initiating event, its frequency we got, and now we have gone on to the now we have to identify the safety system, which is not a big deal, because from the plant document it will be coming and all that. But then we have to understand their processes, how they operate, what are the interlocks, control, those are available. So let's say reactor shutdown system, there are 2 systems. I told you about see, first is redundancy in the system itself, and then redundant system itself. So primary shutdown system failure, secondary shutdown system, they are the 2 independent system for reactor shutdown. Okay. And then reactor cooling function. Primary cooling system is a system which operates the plant and for deliverable. But secondary shutdown system or decay heat removal system, it comes into the action when when there is a deviation, plant is shut down and it removes that heat. And then for accident condition, we have this emergency core cooling system, which will ensure safety of the plant during emergency. Let us say if the break has happened in the plant, then it will come into the action. Now similarly for power supply system, we have a offsite power, then we have if we talk about the safety, and offsite power is a process part of the plant. Then class 3 power, that is diesel generator, emergency diesel generator, class 2 uninterrupted power supply or UPS systems type of system, and then class 1 is battery bank system. But the capacity of these things will, because only they have to take care of emergency loads, so that way it will be reducing, but they have to be available whether it is a DC power supply or AC power supply. Containment and isolation in emergency system. So primary containment, that is which is keeping the plant isolated from other rest of the atmosphere, and then secondary containment, and then emergency exhaust system. Even if something happens, the hazard should go out from the plant. But this is, we are talking about once in a blue moon type of scenario when accident happens actually. And then human recovery action. There are some actions they require for to ensure safety of the, though human intervention is expected lesser and lesser. In fact, after the accident, at least for half an hour, human interventions is not expected. The plant can take care of its own in autonomous mode, ensure safety and all that. But then still, human action form part of the like observation, surveillance, and then if any action is required, this component can fail. So some actions, corrective actions are required. So human action form very important component of recovery. So we are making progress in terms of understanding the PRA. Now when we do PRA, at the outset I will tell you one thing. The 80% of PRA effort goes into, or I would say 70%, it goes into the data collection. Because data collection is a very comprehensive exercise. It requires understanding of the plant, understanding of component failure, its mode, and what can lead to unsafe failure, and then documenting them and refining them. It takes time actually. And then failure criteria can be at the plant level, what we will call as a damage. Okay. So you saw that level 1, it is a core damage, level 2 containment leakages, level 3 is going into public domain. And so this is at the plant level. Then component level, it will be, let us say system level first of all. If the system is not able to deliver its intended function, and that intended function will be so much of cooling flow, or the temperature assurance that was expected, pressure that was expected. So these there are many more parameters that form part of the, or in terms of system level, how many redundancies were there in the system, and discrete event failure like 2 out of 3, this is voting redundancy and all that. So how many system train failure you will call as a system failure. Component level, you have to go to the component failure, like we do failure mode, effect and criticality analysis. Their mode of failure, how long it remained failed, whether it was partially in that condition. Sometimes the partial failure also works for, at least for emergency condition. So we should have a different, and then at the end of the PRA modeling, we have to do a sensitivity analysis, what kind of failure, mode of failure, type of failure, number of failure, and what forms the core risk module of the plant. Okay. And then system level failure, as I told you, minimum component channel and all require plant level. So we started from component level, system level and plant level. Now we have the failure criteria with us, and these have to be documented, because against this criteria we have demonstrated the plant safety. So in this lecture we have discussed initiating event, selection, procedural element of PRA, and role of failures. I am sure after this 1 week, first week module itself, you will be, you would have learned modeling for PRA and all, and that is a very good aspect of these lectures, NPTEL lectures, that they empower you for your future domain areas, how to do the risk modeling and all that. And yeah, so thank you very much.